Miami chapter and all other organizations, they are involved for today's event. Appreciate the invitation that you sent to me as a speaker. And I would like to share my screen. So let me know if you can see.
No, we can't see.
Okay, so just, I believe I'm just trying to do that. Okay, so let me know if you can see it.
Yes.
Do you see it?
Yes.
Awesome. So Nazni, would you please kindly let me know if you see it in like the presentation?
No, it's not. It's not in a presentation mode yet. Yeah, now it's, yeah.
That's good. Okay, excellent. Thank you, everybody. So I would appreciate if you have any questions, you can feel free to stop me in between my talk as well. Or if you can put it into the chat, that's okay. After the presentation, I'll be able to look into those and answer you if I know them. And I apologize in advance if I don't know those, because some of the questions, like you are from the academia, you know the most recent research. So I might go back and ask the experts from my team and then can get back to you on those. So feel free to post them in the chat box. That way I'll be able to follow up later. Thank you. So if you're all okay, then I can just start going through my slides. And first of all, I'm going to turn off my video so that it's like, I just want to turn off the video so that it has the enough bandwidth to play my movies as well. Yeah, I don't see the option now right now. I'm not really familiar with the Zoom, but I'll go start, and if the movies doesn't work, let me know. Then I'll just try to figure out how to stop the video. Okay?
Okay, go ahead.
Sounds good then. Thank you so much, everybody. Let's start. What is the outline for our today's presentation? First of all, I'm going to go over the introduction about the photonics and also Ansys Lumerical. Then I'll talk about a little bit about the products and the technology and how it can help for a photonic designer. And definitely after that, I'm going to do a little bit of applications deep dive, like for the photonics, nanophotonic and integrated photonics, both sides. And then definitely I'll conclude with some of the career opportunities that Lumerical can bring for you. And definitely we will have the question answer session after the talk. So according to Wikipedia, like photonics is the physical science of light, generation, detection, and manipulation. But now I think you might have a question that what's the difference between photonics and optics, right? So optics is something that you see with the naked eyes, but photonics is something that when we talk about it, we are talking about very, very small wavelength scale features where you can, where the electromagnetic wave nature of light is extremely important, as well as like the quantum nature of light, like the photons, they can create electron hole pairs. Those are much more important in photonics than in the traditional optics. It is like you need to see the human eye perception for the tangible world. So that's, I would say, the difference between photonics and optics. First of all, in the photonics, we just divide it into two regimes for Ansys Lumerical tools, how their applications are oriented. First side, we talk about the integrated photonics, which really talks about the high volume, low cost manufacturing made in foundries like Global Foundries, TSMC, etc., the world's leading foundries. And the material choice for those foundries are the silicon photonics, and sometimes it can be also indium phosphide or silicon nitride. On the other hand, the nanophotonic side, it is most likely very small features. It can be the thin film, which has like tiny particles embedded into it. for example, one of our customer, they are the makeup manufacturer. They use our tools in order to design their makeups. So that's I can't tell the name due to the confidentiality, but that's how different is nanophotonics from the integrated photonics. Just wanted to share that example. And in between these two, there is like a gray zone, I would say, where it falls for the CMOS image sensors, displays, cameras, where you can see that they take the processing from the integrated photonics fab. They use the same processing from there, but most of the simulation features that is needed in order to do this type of simulation comes from the nanophotonics camp. So in order to keep them separate, we kind of divided into two parts, like integrated photonics, and under nanophotonics, also we consider the display and the CMOS image sensors as well. So what is like the photonics world changing every day? So if you think about it, like 10 years ago, there was like even, no, I wouldn't say 10, maybe 10 will be exaggeration. If I said 20, that might sound right. So 20 years ago, there wasn't a lot of photonics in this world. So you might have like electronic light bulbs in your home, CRT televisions in your home, and only photonics was used for long haul communication in between cities, right? But what happened nowadays, it's like you have LED lighting in your home, and also you have like smartphones, which has like more than one camera sensors embedded into it. Definitely you have the um, new televisions which uses LCD displays minimum. So these are all the areas of photonics which has been grown in last 2 decades a lot. So they are like the most important space where photonics can contribute a lot is the data center application, because it can enable the bandwidth that the data center needs today. So overall, like what I wanted to say here is like photonics is growing and the field is green, because like every day, every time there are like new researches going on in all of those fields. Here, this one is showing a few numerical application spaces where you can see that first is the datacom, because that's where the major numerical customers are right now from. But also LiDAR is something which is being used for autonomous vehicle application, and another field is emerging that's called quantum computing. If you can go to our website, you will see customer success stories from a company that's a Canadian company. They have like really great success with quantum computing application using Ansys Lumerical FDTD. And there are other applications as well for sensing, image sensors, AR, VR display, etc. This is something that I would like to show you how we are heavily investing in research and development for this photonics field. So if you look into this, you will see that with the time we added new technology in our portfolio, and also the number of publications, number of citations where they directly cited numerical tools increases over time, which means in different areas of applications, it is being used by our user and getting acknowledged. When we come to the ecosystem for photonic integrated circuit technology, we will need our foundry partners in order to give our customers a full, complete workflow so that they can also fabricate those technologies after the simulation, which is equally important as well to get the right design rules and everything. So for that, we are working with our foundry partners who are the world's leading foundries for semiconductor. You can see here, I'm showing some of their names: Global Foundries, TSMC, Compound Tech, IMAC, etc. Now I'll go over the products and technology. So first of all, here you can see that this is a chart where it is showing all numerical products. So here in this section, the photonic multiphysics simulation part, you can see that these are all our component level tools. So first of all, I would like to say a little bit. So when you want to do like a photonic integrated circuit, you need to first design your own components as well. So for using those by using those component level tools, you can design your components first. You can do your optical components using FDTD mode and DGTD FEM. Those are all our optical solvers. And then you can use our multi-physics solvers like charge, heat, MQW. Those are also you can use for different multi-physics applications like optoelectronic or thermal simulations. And then you get your component ready for putting that into the circuit level simulation. So in order to do the circuit level simulation, you have interconnect, which can do photonic integrated circuit simulation. And we also have photonic Verilog A platform, because many of our users, they are comfortable with the Verilog A platform. They come from the electronic industry, and we have the option that they can do the Verilog A platform simulation using our component level tools. They can design the component and they can have the Verilog A model ready for them. And then there is that CML compiler, which is the bridge between the two of those, the circuit and the component level simulation. We will talk a little bit more later with the dedicated slide for the CML compiler. That way it will be easier. And definitely in the right-hand side, where it is showing as different interoperability that we offer with our tools like MATLAB, Python, and Lumerical, it has its own script, as well as we have the integration with different tools like KLayout, MATLAB, Tanner, Virtuoso, ADE, and CMAX, so that our users can pick up what they are comfortable with, so giving them a flexibility in there. And I already mentioned about the foundry partners, so I'm not going to go over again. So first tool I would like to talk about is our flagship tool that's called FDTD Solver, which is a 3D Maxwell equation solver. And that's our optical solver, where you can see the key applications here. It is used mostly also for nanophotonics and integrated photonics both. So the CMOS image sensor, OLED, metamaterials, diffractive optics, and photonic crystals can be similar. Those are the key ones for FDTD. Then I would like to go over the mode solver, which is the, okay, so I think there's somebody waiting in the room. Najin, maybe you want to allow, yeah, sorry. So the mode solver, I'd like to say here that is our waveguide design environment that can be used in order to do the waveguide design, and as well as different fiber design. So if you see here, the key applications for mode solver are like tapers, which are like longer devices that might take a long time in order to simulate if you want to solve the 3D Maxwell equation. But with mode solver, if you want to just see the cross section of the mode, that will be faster for the longer devices and so on. After that, there is that device DGTD solver, which is another optical solver, a much newer one. So that came a long time after FDTD solver, but this gives you the finite element mesh for some of the nanophotonic application, which can be benefited from that, like metamaterials, nanoparticle scattering, which has like a curvy surface, and maybe the rectangular mesh in FDTD is not user-friendly as much as where the triangular mesh in the finite element world is better. So you can use that for doing those, and you will get like a higher accuracy in for your complex structure. Now, this one is also under the multi-physics family, which is also built in the finite element drift diffusion method. That's for the charge transport. And when you have like an optoelectronic device, you need to do image sensors, photovoltaics. You can use those. You can use charge solver with FDTD or mode in order to get the result for those components. And that's also from the multi-physics family. That's device heat. When you need the thermal tuning for a waveguide, you will need mode and heat. So you can get the thermal simulation done by heat, and then you can have the optical coefficients from mode, and then you can make them together to get the complete picture for your component level simulation. So here are some of the applications I would like to show you, some of the movies. Please let me know if you don't see those. Still can't find the way that I can turn off my video. I'm scared that it might not allow me to show that. Okay, so let me know if you don't see it. And my apology for that. Okay, so the building block for integrated photonics is actually SOI waveguide. So this one is our mode solver. I'm going to show you here. So you can see the SEM image of the SOI waveguide. And when it is like what it does actually is it can transport the light within the chip from one place to another. You can compare it with some electrical traces where it is where it is used to guide the electrons, right? But in photonics world, you can see that when the light is propagating through these SOI waveguides, they can go with different modes. They can go with more than one modes, right? You can see it from here that there are like two different modes here. And what happens sometimes is if you are designing a waveguide, which is not curvy, which is like this, the Manhattan style, which is more convenient. It's like more conventional one for the electronic world, Manhattan style, right? So if that's the case for the photons, what will happen? You will lose a lot of light from the scattering. So for the photonic world, we need everything to be curvy, like the top one. And in order to do those designs, it was a bit challenging in the beginning. But now we have partners that Mentor Graphics and Cadence. They make the layouts easier for our customers, which can allow these curvatures. And you can have these designs done by our simulation software, and you can transfer it to the layout design tool for the fabrication. So some other ones here. So when you have like a light on a chip, you might want to split it into two different ways. You might want to collect it into two again later, or you might want to just power into two different places. So for all these things, you might want to like create a waveguide coupler in your chip, which can be done using the solvers that we offer. So if you see on the top corner here, it is showing a waveguide coupler. And then you might want to do a filter, which can be used by a ring resonator here. You see, when the light is coming in, it can go round and round. And what it will eventually do, it will drop some of the frequencies, which is not desired. So this is a popular way of doing the multiplexer, demultiplexer for the data center application. And now this one is another example here of a building block where you want to bring the light in to the chip and then take the light out from the chip, right? So in order to do those, you might want to use a grating coupler. I would like to show you the top view and the side view, that what's happening here when the light is falling on the grating coupler. It goes in, and then you see there is a grating which is very carefully designed. The light falls onto it, and then some of those get coupled and some will pass. Yeah, sorry, I think the movie was finished before I was talking. So you see that the light goes in and some of the lights are moving through the silicon waveguide. It becomes slow because of the silicon's refractive index, right? So that's the light that's propagating there. And these are the cool things that you can do for your integrated photonic application with our FDTD and mode tools, the optical tools. So those are all passives. Now I'm going to talk about, so this one is like an SEM image of a grating coupler, how it looks like under the SEM machine. And now I'm going to talk about the active components that you can design with numerical FDTD mode and as well as the charge and heat solvers. So the multi-physics simulation, whenever it is photonics, it will become multi-physics eventually because there are like so different types of physics are involved in it. So it's better to have the capability of using different solvers from different physics. So here you can see that this is an electrical phase control, which means that when we have a waveguide and we put a PN junction in the middle of it, and what we can do, we can just change the bias voltage, which will eventually change the charge density inside that waveguide, and that will affect the mode of the waveguide slowly. So that is something that's called the electrical phase shifter or phase controller that can be designed with our tools. Like I said, FDTD and charge will be here, something that you can consider. Sorry, if it's a waveguide, it will be mode and charge, not FDTD. Okay, so that's the other one. That's the heat solver can help you. If there's like a thermal phase control, we know that all the like the optical phases, modes, they can be really, really sensitive to temperature. So in order to know those effects of the temperature, you need the thermal heat solver in order to do the optothermal behavior of your waveguides. This one is showing like a photo detector, which is designed with our tool. Here you can see that this is a germanium epitaxial layer that's on top of silicon. So the IR will be absorbed by the germanium, and that's how the light will be going out from there. So in order to get the highest efficiency of the photodiode, we need to the highest responsivity. We need to design it better with the simulation tools that I mentioned. That's charge and also the FDTD. We went through all about the component level tools. So if you have any questions, I will pause now and maybe give you 1 minute if you want to say something about the component level tools. Is there any question? Or if you want me to finish, I can just finish first.
One question on the, why is the adjustment of the phase or the electrical adjustment of the waveguide, why is it slow?
What do you like? Is it from this slide? Is it from this slide? Sorry.
Yes, that exact situation. Yes, go right ahead.
Okay. Okay, so it depends on like how much voltage you are applying, and it depends on the material that what will be the response, right?
Are you talking seconds, minutes, milliseconds, nanoseconds? What units are slow?
I don't have the time scale here. Sorry, I don't have the time scale here. If you want, I can get it. I can know and then let you know about that.
That's
okay.
Fine. That's no
Sounds
problem.
good.
Thank you.
Yeah, no problem. So here is the photonic integrated circuit solver that we all use for integrated photonic circuit simulation. So here you can see that there are like it has the schematic solver that you can design the photonic integrated circuit using our primitive library, which can be edited by according to your component values. And then we also have then you can drag and drop and create those, or you can use your own compact models and put them into this schematic editor and then do your photonic integrated circuit simulation. You can do both in frequency and time domain simulation. You can also use this for doing corner analysis, Monte Carlo analysis, etc. So that's all about the photonic integrated circuit solver interconnect. It has a lot more to say, but it's hard to just describe in one slide. But definitely, if you want to know more, I can share some material which is from our website. Then we can go through those. You can go through those. And I would like to mention here with the interconnect, we also work with our partners called Cadence and Mentor Graphics in order to do electro-optic simulation. So when there is a full system level simulation, you need to also include the electrical drivers in it. You need to have the cadence. And then what it does is like that will have the It's cadence virtuoso. It will does the electrical simulation part and call interconnect in the background in order to do the photonic simulation part. And that way you can have like a full simulation of your electro-optic system. So this is something new that we recently added for our users. So this is called the process-enabled custom design file. So most of our customers, they just don't want to go to the foundry and then get a PDK and then just do their simulation, circuit simulation with the component that the foundry provide, right? So most of our customers, they would like to do their own component simulation. That is their secret sauce for the success. So what happens is like right now, our foundries that we work with, our partners, they can provide you a process file, which you can use with our tools and then just simply change the.
Fatema, sorry to interrupt you. Your voice is like breaking down. I guess maybe there's
okay. Can you hear it better now? I mean, is my headset not working? Is it good now?
I guess not. Hassan, is it okay from your side?
No, I think there's a feedback in Fatma's side. I think like there's a feedback from speaker or something. It's like a humming sound in the background.
Yeah, something like that.
Okay, let me go check a little. Can you hear me better now? Hello?
No, it's the same actually.
Oh, yeah, I thought something with my headset.
Maybe, I guess.
Okay. Can you hear me better now?
No, it's still the same noise feedback I'm getting.
Oh. I just don't understand.
Now it's okay. Now it's okay.
Oh, is that okay?
Thank
Okay,
you.
that's excellent. What I have done is just taking off my headphone and then put it back again. Sometimes that works. That's great. Okay, so I was in the process file, right? Hello.
Yes, you.
Okay, no problem. So I'll go ahead with the process file information. So when like our user, they get a process file from our foundry partners, they can build their own model using that process file, and then they can just do like a 3D geometry using the layer builder that is embedded in our tool right now. And then what they have to do is they can just create the custom component compact model using our CML compiler and put it in the interconnect system in order to do the circuit level simulation. So that way it is a lot easier than creating their own compact models and then making them foundry compatible. So that way it is already foundry compatible because the foundry is providing them the process file. So now I'm going to talk about CML compiler, what that does, and that's the newest addition in our tool family. So CML compiler is something that integrates, like it is a bridge which is connecting both component level simulation engineer and also the circuits level simulation engineer. So when a component level designer, they create a component, that they have to make sure that it can be in the circuit environment, it can be like they have to make a compact model in order to put it into the circuit level environment, right? So in order to make those compact model, you can do it manually, but when you have like libraries, different versions to control, it just become a lot of tedious process that if you have to do it manually. So it CML compiler, what it does, it can give you it can automate this process. It can automate the CML generation on behalf of you, and it will make your life easier with keeping the different like versions and libraries updated and organized according to your choice. And what it does additionally is it can give you different compact models for different tool of your choice. So you can generate interconnect compact models. It can also generate the virtuoso symbols, which is like I think popular also in some of the users who are from the electronic industry. And it can also create the photonic Verilog models as well for using in the virtuoso environment. So here is one, so those everything were for the integrated photonic side. So now I have a few slides, I think, on the nanophotonic side of our applications. So here, this one is the most popular one, the CMOS image sensor. You can see here the picture of like this might be a little bit older picture, and you can see the SEM image of it. So where we can see that when a light comes in, so this is the workflow that you can do with the Lumerical FDTD and charge in order to optimize your design for your CMOS image sensor. So you can see when the light is coming into the object, we can use FDTD in order to see the optical efficiency and the generation rate by how much the silicon is absorbing the light. And then after the optical efficiency, we can bring those to our charge solver, and you can calculate the quantum efficiency and crosstalks between different colors of the pixels. So those can be done using this FDTD and chart solver. There are a few movies I'd like to just play those in case they don't go. Please forgive me. Maybe the bandwidth is not great from my home. And so you can see that these are the CMOS optimization that most of our users, they would like to do, and they just don't want to, they want to make sure as well that like it goes through the light, that it goes to the right filter and it doesn't go between green and red, I mean, which is not desired, just the particular filters that need to be it should go through those. So those are the important aspects of the simulation that can make sure that your design is going to be correct. This one is another nanophotonic application. This is for the world where we want flat optics. So you see metal lens that can be designed as well with FDTD. So this has no curvature here, but it will make a lens type of behavior from these tiny little nanostructures you can see, and you can definitely do the simulations in order to optimize the structures and get your metal lens ready for the application. So this one here, I just wanted to show you how we can connect the nanophotonics and the traditional optics together. So whenever there are like microscopic and macroscopic, it's in this macroscopic world, if you have like a system where there is also a microscopic component, like for example, a grating coupler, and you would like to bring that design information in order to see how it looks when it comes to the macroscopic optics world, you would like to do the grating coupler simulation using FDTD, and then you would like to see the whole thing from human eye perspective using Ansys SPOs, which is our optics level solver. So you can see that you can run this using the Lumerical FDTD for the nanophotonic side of it. And you can import the surface optical properties, volume optical properties, and the spectral intensities, distribution, races. You can import those data to the macroscopic scale and see the whole behavior of the device. Now it's all about the career opportunities that Ansys Lumerical can offer. But I would like to mention here as well that as Lumerical users, you already have like uh, good job opportunities, career opportunities in the world of photonics industry, where they would like to hire photonic engineers. You can see job postings, they directly mention that from renowned users, that like our users, I just can't say their names here, but you will see the job postings. They mention that they would like to have like an integrated photonic design engineer who has experience with Lumerical, because most of the world leading industries are using our tools in this sector, photonics sector. But so you already have the, as a Lumerical user, you will have this job opportunities over there as well in our customer base. And then you will also have job opportunities definitely within Ansys Lumerical. So like I said, if you have an engineering background, there are like few like divisions that you can have job opportunities according to your choice. There can be like R&D division where you can contribute into the physical solver part. So you can join to the R&D lab, which we mentioned that because it's the physics-based team, and there is the R&D engineer, which is from the more from the computer science background, and they goes for the like the software's basic invention part. So like you can go either way according to your expertise. And then there is sales, where you will need somebody like me, the product sales manager, who knows about all the products from the top overview, but you know the people as well from your team. So whenever there is a deeper dive needed, you can bring those proper person and get their expert opinions, but as well as you have to figure out what your customers need as well, so that you provide them the right customer support with the right product. And then that way they will be like getting benefit of the simulation they need, and they don't have to look for like 10 different tools and then figure out on their own. So that's mostly it's about. Or and then definitely you are the face for the customer. I can talk a lot more about the sales side because that's what I do. So you are also the customer facing person, so you get a lot of customer feedback on what the features that they would like to see from your tool. So you can definitely provide those requests anonymously in the R&D division, so that those features can come out. And we do like 2 major releases every year, where we try to put priority to our customers' request in order to give you what you need in order to be successful for your photonic simulation side. And then there is that marketing division, where you can be the product marketing manager, which is another fun job to do. And you would like to connect with people as well and do some more product marketing on that side. And there is another very, very important role as well, that's called the support engineer. And that is also called applications engineer in Ansys. So now it is applications engineer also for Lumerical, where you have the expertise on as solver, which you answer all the questions to the customers when it comes to the customer support. So for example, we also provide premium support with our tools for our customers. So whenever they have any problem with their simulation setup, or like how the examples they are seeing in the website, that they need a little bit hand holding on those, and they might want to optimize the speed of their simulation, they can come to us. And then one support engineer will be going with them to do the assistance with those projects as well. You don't have to tell us directly what your project is. You can just give us a general idea or some example from our website, which we can explain to you and then help you with those. And for sure, there will be some other job opportunities. That's why the link is here. I can share it in the chat as well. So you can go there and definitely check what are the current job opportunities that is coming with Ansys Lumerical. It is based in Vancouver, BC, but like I want to mention now, because that's now Ansys with Ansys, so you can be like in US, and then I think that employment opportunity is open now, and like maybe the HR can consider. So if there is a need for a position in some of the states that can be also hired if there is a like opportunity for that. I believe that was everything from my side, and I'll be happy to answer any question that you might have.
So far, we have two questions in the chat box. One is it possible to simulate transistor-based circuits along with the photonics integrated circuit?
So if it is that like you want to do the course simulation, then I think I already did that. You can use like Cadence. If you're trying to use the circuit simulator from Cadence, that is possible because we have the course simulation opportunity with Cadence, right? And the second one is what kind of source did you use for flat optics? So there are like different options. So you have to, like on top of my head, I don't know for what is used for the flat optics, but I can definitely send you some links with the example from our website, which you can see. So there are different options for the sources, and you can pick up whatever you would like to see.
So if anyone else have any questions, they can unmute yourself, or you guys can also send the questions in the chat box. In the meantime, I have one question.
Yes, please.
Regarding the material section of the numerical FDTD, there's an option to select like plasma materials. So in there, we have to put like three options, like permittivity, then plasma frequency and plasma collision. But sometimes it's really difficult to like figure out, is it like how the material defining is happening over there.
So you have the parameters, right?
Yes, I have the parameter.
Yeah, and then you just import those in FDTD.
Yeah, so how like we try to understand like how Lumerical is defining the whole material using this parameter only.
Oh, so those that's a good question. So that you need to see the solver physics. I can send it to you, the FDTD solvers. So if you take a look, but if you don't have, if you still don't get that, definitely we can follow up. I can follow up and talk to you. That's a little bit broad for this.
That will be great actually, because we tried like so many simulation using this parameter, and my advisor is also like he has these questions in mind, like how FDTD is defining using these three parameter. It's like a little bit confusing for us. Like, is it properly defining the parameter? Because if it doesn't, that time the simulation result is not trustworthy. So
of course, yeah, no, for sure. So there are some physics definitely behind it. So the solver physics is important, and then that's what you need to know about that. And like another thing I would like to mention here, that like for the what material exactly, Nazneen, can you share with me what material you were?
Most of the time we use like graphene.
Okay, graphene, right? Yeah, I think we do have examples with graphene in our applications gallery. So what happens is like when we do like a simulation example, we do like benchmarking with some of the experimental results or like something published, right? In order to make sure that what we are seeing is correct parameter wise. I think that's material parameter wise, that will be the best thing to do. So like definitely there are like proof points that can be validated with like simulation and some experimental results. So definitely it's a good one. And then I thank you for asking me that. And definitely I will follow up with you with the link for the example with graphene, and as well, like if it is possible, the solver physics, because sometimes it's not always obvious how it is using. So I'll definitely discuss internally and see what I can get for you.
Thank you so much.
No problem.
I guess there is like another question, maybe. There's the TNT resource. Oh, okay, no, it's not a question. I'm sorry about that.
No problem.
I have one more question actually. So there's like one paper, and we try to like replicate the same the paper using the same parameter that they have uses, but sometimes in simulation, what we get, like it doesn't exactly replicate the same like results. Sometimes it varies like so significantly. It's like that time it's like little bit confusing. Like Like how can like it's not repeatable. That's what like we felt for some of like replication of our like papers. So how can we make it like workable? Like, is there any way to make sure that it's fixed over time, no matter like how many times and from which computer, from which software I'm using it, but the result should be the same, right?
I accept what you're saying, but the thing happens is there can be many things that can make the result off a little bit. So what happens is even with our version, so if you are using like an older version, you can get a little bit different result with a newer version because of the rounding errors and many things that can change with the time and the versions as well. So I'm not sure whether you are trying to reproduce experimental work or like a simulation work. You are trying to reproduce a simulation.
It's a simulation work, the same work like our ex-student produced. I was like trying to replicate that result, but that time using the same software, same version, but still there is like the result shifted so much. So it's like
so much. Yeah, so much is not. I think there should be something that we can do. Definitely, maybe some of the conditions you need to check, meshing and different things that can affect the simulation result. So that needs to be checked carefully. So if it is the same version, same software and simulation result, then definitely I would request maybe check what else can be changed. And if you're using FTTT, you can definitely request a support ticket or post in the KX. We also have like the online platform that's called Knowledge Exchange, which is mostly popular for the students, graduate students, and we actually appreciate the help from them as well, because they sometimes just post their findings, and that way it can be helpful for many other students there, right? So if you still see this problem and that's from one of our tool, not necessarily FDTD, feel free to post it there. And then definitely if there is no question, no answer from any students, one of the support engineer is going to answer you. So I'm sure there are ways that you can optimize it and then match the results if it's the same software, same version. And even like if it is like an older version, it shouldn't vary like a lot. So there must be something that you need to adjust.
Thank you so much for your answer. So there is one question from Daniel Peters. Is full functional extended use student version of Lumerical available, not for the 30 days trial? If
yes,
what is the
academic, he means academic, right? Academic
yes, yeah.
Yeah,
student
of course.
version, yeah, it's academic.
Of course, the academic licenses are definitely available. And if your university, if you're from an university, I believe, let me know what's the name of the university.
I don't know. Daniel, can you please say the name of the
Yeah, can you unmute, Daniel? Like, what's the university you're from?
Yes, the independent researchers. This is a new field. It's not fully available everywhere, and I don't have access to a university that would be teaching that. So, is it possible for an independent researcher to try the student version?
It's unfortunately for the independent researchers, if you don't get the affiliation from a university, unfortunately, you have to go for the commercial license. You can go for a short-term one, but like 3 months, the shortest, but I'm sorry, there is no option that you can have the academic version, because for the academic license, you will need to be affiliated with an university. You have to have like an email that's from the university, and the purchase order needs to come from the university. So we know that it's going to be used for academic research and will be published in the public domain.
Okay, thank you.
No problem.
So is there any other question from the audience?
Hi, this is Saiful Islam. So I had a question.
Yes, please.
So actually, what I have seen during the simulations, so if there is any possibility of getting, if the situation is like this, that my solution is not converging, at that time I see some warning comes that your result is going to be diverse, something like this, or your result is invalid. So is there any relation of this thing with the auto shut-off level? So do I need to, my main question is, do I need to bother the auto shut-off level during my simulation or after my simulation?
So the auto shut off, sorry, if I just want to make sure that I understand your question correctly. So the auto shut off, like when does that happen? If it is like less memories, that you don't have access to enough memories to do the simulation?
No, actually I'm telling that my question is like this, that is there any reason that...
Yes, I understand your question, sir.
Okay, just is there any relation
Yeah,
of
yes,
level?
sometimes it has, because I also face the same kind of problem, because while you do the simulation in a FDTD or like some other numerical software, if the auto shut off level is not, normally it's the default, if you're like, we are using the default auto shut off level, right? But sometimes you have to like uncheck this auto shut off label if you're having this warning sign that the simulation is not converging, it's diverging, and then you may run the simulation again. If still you are having some problem, you should have to check your parameters, that those parameters are okay or not, because sometimes because of the parameter error also you will get this kind of message. So that's just like a solution we have applied so far if we have this kind of problem.
I have got your point. Okay, so suppose at any situation I'm not getting the warning, okay, but I'm getting, so do I need to consider auto shut off level for getting precise result?
Yes, in some of your simulation, not all of your simulation. In some cases, you need to consider this auto shut off level. Because after the simulation, there is a one text file generated, and you can see like how much time the simulation took, right? If it's converging, that time the time will reduce. If it's diverging, the time will be like irregular kind of thing. So immediately you have to think like, I have to uncheck this auto shut off level, and then you can run it again. Like after each simulation run, you can check the like run file and see like the time is converging or diverging, even if you're not getting any error in the main simulation file.
Yeah, I got it. Is there any specific number with the help of which you can just compare? Suppose if I get at the end 0.02 or suppose 10. So by watching this number, can I come to any conclusion that my result is comparatively better or worse? With this number, does it matter after the simulation?
What number? It's the simulation time, you're saying?
No, auto shut off number. Suppose auto shut off 10 to the power minus 3, another is 1 or 10. So what's the difference between auto shut off number 10 and 10 to the power minus 3?
That doesn't have, like, so far in my knowledge, maybe I'm not be the right person to answer this, maybe Fatema can answer better, but as per my experience with this Lumerical software that I checked, like there is like you can play with this parameter and try to figure it out, but there is no direct relation. But you can uncheck this auto shut off label while running the simulation and while it is diverging. That's what I know, or that's what I did while I got this kind of error. So I don't know the direct relation. Yeah. Fatema, can you answer? Help me over here.
No, thank you so much, Nazneen. Thanks for your answer. And I must say that you are a better user today than what I am, because I don't open the software every day and don't do the simulation anymore. I have done those in my early stage, right? Right now, I'm not doing it every day. So you are a better user today for numerical for sure than me, and I think you answered the question correctly. It's a lot of trial and error type of thing that you have to do for this kind of situations, but Saiful, like if I understand correctly, also I would like to encourage you maybe just do a quick search in the knowledge exchange, because sometimes these things are posted there already from some of the users, and that way you will get a quicker answer. If you don't have seen anything there, you can post it there, and then definitely one of the support engineer can get back to you on that. And my apologies, I just have another call to jump on at like my time 1 o'clock, so I have to leave now. I'm so sorry about that. So sorry to take so long that we have like less time for discussion. Sorry about that.
No, it's okay. Thank you so much for joining with us, Fatema.
Thank you, everybody.
For attendees, if anyone has any more questions, they can reach to me. I will collect this question and send to Fatema, and she will come back to you guys later. So
yes, definitely. I'd love to follow up with the questions that you might have, and then that needs some additional materials. Nazin, feel free to send me an email, and I'll be happy to follow up with those. Thank you, everybody.
Thank you, everyone. Have a great day. Bye-bye.
Bye.